4.2, my version of it. Let's see, first thing, reminder, if you can think of some way I can make this more enjoyable for you, please let me know. Just text me, let me know. Second thing is that last problem of Thomas's about magnitudes of stars. Remember that Sirius had a positive 1.45 magnitude. Our sun has a 4.8 magnitude. So Sirius is a much, much brighter star. The computation is done like the difference between a 1 star and a 2 star is 2.512 squared. And it keeps going up, like the difference between a 1 star and a 3 star is 2.52 to the third power. We've got approximately a 1 star to almost a 5 star. So a 1 star to a 4 star is a difference of 2.512 to the fourth power. So about 40 times more powerful. This is almost a 5 star, our sun is, and Sirius is still just a 1.4, so it's not exactly a 1, but Sirius is like 40 times more powerful than our sun. So the next nearest star, I'm saying that now, and no, Sirius is much closer to us. This is all news to me. Sirius is much closer to us and much, much brighter than our, much, much, much brighter. That don't make no sense, but I know it is brighter by about 40 times. If this was an astronomy class, I'd have this down a little bit better, I hope. Second thing, I want to show you something I do know something about, this exponential curve. I added to my growth chart. Here we've got, here's where we started. I talked to you about it in Thomas's 4.2. Here we were on the 22nd or so, 23rd, 24th, and 25th. So that is an incredible jump up, just an incredible jump. You see, I'm not sure you can see all of that because it does go so high, which is why you'll see some chains over here, let's say on the y-axis logarithmic detail, because they can't fit all this into one graph reasonably. So those are the numbers. That's what we're dealing with right now. Good luck to us. Okay, let's get going on my 4.2. Okay, number 1, 2, and 3, they're asking you to rewrite in exponential form. So number 1, 3 equals log base 4 of 64. We're not used to looking at it like that. I'm going to move the answer over to the other side. So equals 3. Now it's saying, what do you raise 4 to make him be a 64? What power, what exponent do you put on 4 to make him be 64? You can rewrite it like that, which is what we're asked to do. 4 to the third power equals 64, and we're good. That's all they want you to do there. Number 2, log base 8 of 64 equals y. We're saying, what do you have to raise 8 to make him be a 64? Remember, this is the opposite function of exponentials. So we can turn this into an exponential. 8 to the y equals 64. That's what they want you to do. On your number 2, we know that y would be a 2 there. 8 to the second power would be, it gives you 64. So log base 8 of 64 equals 2. Remember, the exponent is always across the equal sign. The exponent is always the answer in a logarithmic. Logarithmic equals, there's the exponent. Exponent is always the answer. Number 3, log base 6 of x minus 1 equals 2. They're going to want 2 things from you here. The first thing that they want from my math lab is for you to rewrite it. So we've got a circle happening. 6 squared equals x minus 1. That's what they want from you first. Then they want you to go ahead and solve for x on this one. So this is rewritten in exponential form because there's our exponent being an exponent. Now we just take it further. 36 equals x minus 1. We're trying to solve for x. So you're going to move 1 to both sides. X equals 37. So that's 2 steps on that number 3. They want the rewritten and then they want the answer. I don't believe they wanted it here, but if they do, it's Y equals 2. 4, 5, and 6 ask you to rewrite in logarithmic form. So we're going to be putting the word log into each one of these and rewriting it in its opposite format. So the problem says 4 to the third equals 64. Put a log. The base will be the base. You know the exponent is always the answer in an exponential. In a logarithmic, the exponent will always become the answer. And 64's got to go somewhere. So that's saying, what do you have to raise 4 to make him be a 64? You have to raise him to the third power. Number 5, we've got the fourth root of 625 equals 5. Your brain needs to know that this is going to be 625 raised to the 1/4 power. You've got to transfer it to that kind of an equation with an exponent before you can write it as a logarithmic. So log equals, the base is 625. The exponent will be the answer, always in a logarithmic. When you're rewriting as a log, the exponent will be the answer. 5's got to go somewhere. So what do you do to 625 to make him become 5? You lower him by 1/4. You take the fourth root of him. Okay, let's look at number 6. Number 6 is p to the third power equals 1250. Again, rewriting it, write a log. The base is p, put it down there, a little bitty p there. The exponent will always be the answer, and 1250 will go right there. So it's sort of like, what do you have to raise p to become 1250? Or what number would p be if you raise it to the third power would give you 1250. So what number could you raise to become 1250 by raising it to the third power, which is what was written there. They're done. They don't want you to solve that. They just want you to rewrite it. Let's see. Okay, the next problems, 7 through 15. On 7 through 15, they ask you without using a calculator. So let's look at how to do that without using a calculator. In this class, I can't envision where you will be asked to do it without using a calculator, but I think it's super important that you understand it and that you're able to do it with your calculator and without your calculator, because there'll be other problems where you can't use your calculator. So let's go through those. Let's see, number 7, evaluate. Log base 2 equals 1024. So let's set it equal to x, since we're trying to find what the log base 2 of 1024 is. Let's do that kind of thing. 2 to the x equals 1024. Now, if this were a little bit simpler problem, you would know what it was. For instance, if the problem had been log base 2 of 8, you'd put an equals x. You could say 2 to the x equals 8. And you probably could figure out that 2, 4, 8, 2 to the third power, so x equals 3. But they're asking you not to get to 8, they're asking you to get to 1024, and that's quite a jump. That's not something that I would expect you to know just right offhand. So let's use our calculators. And if you have a guess, this was 2 to the third is 8, so we can tell it's going to need to be a lot bigger. So let's try 2 humpy 8 and see what happens. That's only 256. If we double that, that would be 2 to the 9th, and that would give us 500 and some change. And then we go up again. 2 to the 10th would give us 1,000 and some change. So let's check that. 2 to the 10th is 1024. So x is 10. Log base 2 of 1024, what do you have to ratchet 2 up to? What exponent do you have to lay onto 2 to make him be 1024? That would be a 10. and we use the calculator there. We don't know a way to figure this out without just hunting and guessing. We will figure a way in a couple of sections, but we don't know it now. Log base 2 of 1 over 128. So again, we're looking for an answer, so let's say equals x. Let's set it up using the circle. 2 to the x power equals 1 over 128. I know if I'm going to move the 2 to the denominator, this x is going to have to be a negative. It's going to have to say move me, move me, move me. So I know it's going to have a negative on it, x equals a negative, but I'm also interested in how do I get from 2 to 128. So we know that 2 to the third power is 8. It's going to be bigger than that. Let's just try some. 2 to the 6th power is 64. I need a little bit more. I need double that, so that'll be 2 to the 7th. Just multiply it times 2 again. So there's where we get to 128, raising it to the 7th power. Don't forget we need a negative on there to move this numerator down to the denominator. So again, we're playing with the calculator just because we're not that familiar with the 2's. I mean, we could write them all out, but that's just not going to happen today. Number 9. I've got notes, but not for a while, that I need to watch out with for you because my math lab does some weird stuff later on. Let's see, let's look at number 9. Log base 12 of the square root of 12. Again, we're looking for what is the exponent that we have to raise 12 to get the square root of 12. So let me put an x there, and let's set this up. So 12 to the x will give us the square root of 12. I'm hoping that you're kind of getting the hang that when we have a radical, we need to change it to a fractional, to a rational exponent. So leave this side alone. You know that the square root has an understood 2 there. So this is raising 12 to the 1/2 power. So we have our original 12 to the x power will give us 12 to the 1/2. When the bases match, the exponents match. So x is a 1/2. 12 to the 1/2 will give us 12 to the 1/2, which is also square root of 12. All right, let's look at number 10. Log base 81 of 3. Again, if we're looking for something like that, let's set it equal to x. Let's do the circle. 81 raised to some power will give us a 3. This is a great reduction here. We're going from 81 down to 3. So this is going to need to be a fraction. So let's say if it were 81 to the 1/2, you know that means the square root of 81. Well, the square root of 81 is a 9. We need it to be a 3. So you're just still thinking, what root of 81? 3 times 3 gives you 9, times 3 gives you 27, times 3 again will give you 81. So if we do the 4th root of 81, there we'll get a 3, because 3 times 3 times 3 times 3 will give us that 81. 3 times 3 is 9. 3 times 3 is 9. 9 times 9 is 81. So what do we have out of that? 81 to the 1/4 power will give us 3. So there's our answer. X equals 1/4. What do we have? What exponent do we have to slap onto 81 to get it to be a 3? That's a 1/4. You can play with your calculator somewhat. If you're happier using your calculator, you could do, try square root of 81. You're trying to get a 3 out of that. Nope, not good enough. Clear it. Let's do cube root. That's a different key. So, oops, I forgot. Got to tell it cube root is what I want. And then cube root there of 81. And that's a mess. That's no good. So let's look at the 4th root. I want the 4th root of 81. And that gives me a 3. And there we go. 81 to the 4th root. The 4th root of the 4th root of 81 is a 3. So x is a 1/4. Okay, let's look at number 11. Here come some of those ones that are just based on principles. Log base 8 of 8. What do you have to raise 8 to make them be an 8? If you're not sure of that, let's set up the circle. 8 to the x equals 8. Well, that's just going to be a 1. 8 to the first power. So the exponent that you have to raise 8 to make him be an 8 is a 1. Number 12 is another one of those little sneaky ones. Log base 12 of 1. What do you have to raise 12 to make him be a 1? If you're not sure, set it up with an x. Do the circle. We've got 12 to the x power equals a 1. If we do 12 to the first power, that gives us 12. That's too big. We need smaller. 12 to the 0 power will give us a 1. Remember, anybody raised to the 0 power is going to give us a 1. So the exponent is a 0. So log base 12 of 1 equals 0. But they're looking for the 0 there. Number 13. Log base 7 of 7 to the, I messed that up. Log base 7 of 7 to the 6th power. What do you have to raise 7 to make him be 7 to the 6th? So if you're not sure of that, set it up. 7 to the x equals 7 to the 6th. When the bases match, the exponents match. So what do you have to raise 7 to? Down here. What do you have to raise 7 to make him be 7 to the 6th power? You have to raise this 7 to this 6 to make him be 7 to the 6th. It's kind of a sneaky problem. You can see some tricks there. If you're raising a base to this, grab the exponent. You won't need to be an expert on it. There aren't a million of these. Let's see what we got with number 14. Got log, nope, we don't have a log. Got 9 raised to the log base 9 of 6. So this is an exponential statement. There's no log sitting on the ground like with these have logs on the ground. This is something raised to an exponent. So let's convert it to a log problem. Let's go the other way. They give it to us one way, let's go another way. So anytime we're converting from an exponential to a log, what we need to do first is grab the base and put it down there. The exponent is going to be over here. That's the entire exponent there. And then if we set it up as equal x, we've got the x right there. So we're saying we've got the log base 9 of x equals the log base 9 of 6. When log base 9s match, x equals 6. So don't forget to put the equals x there when you're looking for the answer. Number 15, we've got log base 5 times log base 2 of 2. Okay, so let's figure this piece out first. What do we have to raise 2 to make it be a 2? So let's just take that piece apart here. Log base 2 of 2. Put it x, zip it around. 2 to the x equals 2. What do you have to raise 2 to make it be a 2? It's going to be a 1. So this is a 1. So now we have log base 5 of 1. And we're trying to solve that. So let's set it up as equal x. 5 to the x power equals a 1. What do we have to raise 5 to make it be a 1? Going to have to raise that to a 0. So the complete answer, we did the parenthesis first and we got a 1. And then what do you have to raise 5 to make it be a 1? You have to raise it to a 0. So that answer is 0 there. Okay, number 16, doing some graphing. I'm doing 16, 17, and 18 are graphs. The rest is just thinking stuff, math stuff. Okay. Okay, on number 16, we want to graph the exponential f of x equals 3 to the x, and then we want to graph the log g of x equals log base 3 of x. So those are inverses of each other. It'd be like graphing, well, I don't know if you can graph 5 times 4 and then looking at 4 times 5, or looking at 20 divided by 5. Multiplication and division, adding and subtracting, exponents and logs. So let's start by graphing this one. This was 4.1 when we did this. The x is the exponent, so where the x is the exponent, we're going to be putting the our little series of numbers over here. 3 to the negative 2, it's going to be 1/9. 3 to the negative 1 is 1/3. 3 to the 0 power, 3 to the first power, and 3 to the second power. So let's graph that one first. Got negative 2, 1/9. That is not a negative, it's just the tail of the y. So negative 2, 1/9. Negative 1, 1/3. 0, 1, 1, 3, and 2, 9. Got this horizontal asymptote. We're not going beyond the x-axis. And that's f of x. That's the exponential. Sorry, yeah. That's the exponential graph. Now let's look at the logarithmic graph. In order to do this logarithmic graph, I'm going to move this guy over here and call it y. Do a circle. So we get 3 to the y equals x, just like we were doing in Thomas's set of worksheets. When the exponent, whatever the exponent is, whatever variable it is, that's where you're going to put negative 2 through 2. So the exponent is y. So we're going to put our little set of numbers under the y column. So we're saying 3 to the negative 2. 3 to the negative 2 is up here. 3 to the negative 2 is 1/9. 3 to the negative 1 is 1/3. 3 to the 0, 3 to the 1, and 3 to the second power. So let's see what we've got there. We've got 1/9, negative 2. 1/9 down to negative 2, right about there. 1/3, negative 1, something like that. 1, 0. 3, 1, 2, 3, 1. And 9, 2. So remember, this one's got a vertical asymptote of x equals 0. It's got a vertical asymptote of x equals 0 going on. This is g of x. That's the logarithmic graph. Note that these two little guys have got that y equals x thing going on. These are inverses of each other. Multiplication and division are inverse operations. Adding and subtracting are inverse operations. Squaring and unsquaring. And exponentials and logs are inverse operations of each other. They're reflected across the y equals x line there. All right. I think we're good on 16. Let me see my notes because we get weird fast here. Number 17, when you go to graph 17, yeah, I think we're good on 16. Okay. Let's look at 17. Okay, we want to graph g of x equals log base 5 of x plus 4. Ask you to find vertical asymptotes. I shouldn't have pluralized that, although sometimes we have more than one, but in this case we'll only have one. Domain and range. Okay. Let's look at what we're doing here. If we're going to figure out, let's first look at log base 5. And we've got this y equals here. Let's move it over here. So we're going to do 5 to the y equals x. on our graph. Anytime the exponent is a y, we're going to put our little numbers over here. So 5 to the negative 2, negative moves it downstairs and then square it. So that'll give us 1 over 25. 5 to the negative 1 will be 1/5. 5 to the 0, 5 to the first power, and 5 to the second power. So that's what we want to graph. Actually, that's not the one we want to graph. Let me think if MyMathLab asked you to do that. No. They want you to go ahead and transition, but I want to show you that one just as a transition. And you'll be asked to graph it yourself. So let's graph this one first. 1/25, negative 2. So go out barely and go down negative 2. Then 1/5, negative 1. 1, 0. 5, 1. And then way out here, 25, 2. Okay, so this guy has got, let me see what we're going to do. Okay, good. This guy's got a vertical asymptote of x equals 0 running right through the y-axis. So that's x equals 0 line. That's his vertical asymptote. The domain would be 0 to positive infinity. It doesn't, there's nothing of that graph over here. It goes all the way out to infinity. The range here goes all the way down there. So it starts at negative infinity and it'll go all the way to positive infinity. We're not asked to graph that one. You're being asked to graph this guy. So you know this is a liar. It's going to go 4 to the left. So we're going to take this belly button here and move it 4 to the left. 1, 2, 3, 4. And it sets us up right here with the belly button. This guy's going to go 4 to the left. 1, 2, 3, 4. This guy's going to go 4 to the left. 1, 2, 3, 4. And then drop this guy down. So this is the graph they want you to draw. That's g of x. And then it's got a vertical asymptote right there of x. Let's see, the vertical asymptote is at x equals 1, 2, 3, 4 because we went 4 to the left. So it's at x equals negative 4. The domain will be the same. No, it will not, because the domain doesn't start at 0. We back it up. The domain here starts at negative 4, and of course that's going to be a parenthesis because it doesn't touch this. It goes down and hugs, 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 but never gets there. The red line continues on to infinity. The range, this goes all the way down to negative infinity. This goes all the way up to positive infinity on the y-axis. Okay, so that's simple enough. Maybe it's not so simple, but wait till you get hold of MyMathLab. You are going to have to grab the log. Okay, on MyMathLab, when you click on the graph, up pops some tools here. The log tool, what does this look like? That's the log tool. That's the one you want to grab. So you'll pop that in there. I believe when you pop it on the graph, they're automatically going to take it to the parent graph. So no matter what you do, you try to pull it over here, they're going to pull it over here, and they're going to bring up that table that talks about horizontal and vertical change. So you want to go -4. This one's a liar. So on the horizontal change, you want to put in a -4. So it'll scoot it along the horizon 4. I think that is it. Oh, no, that's the most important part. The other thing you have to do, and it tells you, if you read the directions, you'll see it. I didn't, and so I had to fumble my way through. You've got to also put the vertical asymptote on there. So you go back out and you grab this original set here, and in here it has lines. It has a shape that, is for a line. So you put it there on the -4, and then you've got to put it another place so it will do a solid line there. Check over here, it asks you for solid or dotted, so you want the dotted one. So by that time, you've got your little log going on there. So you'll have both things going on there and you'll be set. Then you hit check my answer to make sure that you have used the log tool correctly, moved it over 4 or how many ever you're supposed to move over, and put in your vertical asymptote. So you've got to do that with a dashed line using the line symbol. Using, if you want to draw a line, I think it looks something like that. To put it on there, don't forget, you need to start it and you need to stop it. And they have little blue circles there. Ignore the circles, no big deal. You just need 2 places for them to get the idea that yes, indeed, you want a line there. Then check your answer. Then it will ask you for domain and range and vertical asymptote maybe to write it out. If you get stuck, if on any of these problems in MyMathLab, if you've mucked it up somehow and you're not happy with your graph, or they tell you what's wrong and they give you an X and you're done with that problem, then do not waste your time putting in a vertical asymptote, domain and range on it and struggling with that, knowing you're going to have to go back and correct your graph. Put in anything. When it asks for vertical asymptote or domain and range, put in your favorite letter, so put in a P in there if that's your favorite letter and hit check my answer, check my answer, check my answer. It'll exit out, go to the next piece, whatever that is, if that's domain or range or vertical, get all those X's quickly so that you can get completely out of that problem and end up with a similar question. So to start over, now that that you've gotten the hang of this piece. So that's a little bit tricky, I think. Let's keep moving. Let's look at number 18. I believe number 18 will be very similar in that you'll have to draw the log tool, use the log tool to draw it in, change its placement by using the horizontal asymptote, and then don't forget the vertical, by using the horizontal shift, and then don't forget to put in the vertical asymptote. Okay, let us look at number 18. Yeah. It's a similar transformation. Let's see, number 18 is asking you to graph h of x equals -4 plus log base 3 of x. So let's start with the basic. Log base 3 of x equals y. Do the circle, 3 to the y equals x. Let's set up our tables. Because the exponent is a y, that's where our little series of numbers goes. 3 to the -2 is 1/9. 3 to the -1 is 1/3. 3 to the 0, 3 to the first, 3 to the second. So that's going to give us a graph. (1/9), -2, 1/3, 1 0, 3 1. It's all high. Oh, I see what I've got going on wrong. Let me start over. Um, 3 1 and 9 2. Because that's a basic. MyMathLab doesn't care about that. What they want you to do is to transform it. This -4 is not attached to the x. It's a vertical up and down, and it's a -4. So that's telling us they want us to take this graph and move it down 4. So easy enough on this little graph here. I'm going to take this guy and move him down 4. 1, 2, 3, 4. That'll move this one down 4, this one down 4, this guy 1, 2, 3, 4, and this guy 1, 2, 3, 4, doing something like that. Okay, so that is h of x. The asymptote is this x equals, the vertical asymptote is x equals 0 line, doing that kind of thing. The domain is what do you use up on the x-axis? We don't start using up the x-axis until 0, and we don't hit on 0, so be sure to put not a bracket but a parentheses to infinity. Range goes all the way down and all the way up, so -infinity to +infinity. You'll need to do the same thing for this one on MyMathLab, as I recall, that you are going to have to first ask for, click on the graph, and then ask for the log tool that looks like the shape of a log tool. Then you're going to pop it onto the graph somewhere. It will adjust it and put it where the black one is. You then need to move it down. So when you do that, I think that automatically pops up, and it's got a vertical change, and you want to say down 4 to scoot it down 4. Then don't forget, you got to put in the vertical asymptote. So go back out, grab the line from the toolbar, and then put it on this line. Hit right here, and then one place, and then some other place. 1 and 2 places. 1 up there, 1 down there. Doesn't matter. 2 places to let MyMathLab know you want that line, and then be sure to mark it that you want it to be a dashed line. Check your answer, and then you'll put in vertical asymptotes, domain, and range. Again, if you mess up on any one little part of that, be sure, just screw up. Just make it so that you don't waste time coming up with those piece answers. Just put in anything. Put in a 7 if you want to, and hurry your way through that problem to get a similar exercise. So this one's going to count a lot. I wrote you a note in announcements about that. Tanisha had a problem she was asking me about with 3.5, where it looked like she had almost nothing done, when in fact, if you open it up, she had just a little bit of 14, 15, and 16 to do, and she'd done all the others. Well, that's because, as I explained in announcements, each one of these, this graph, the vertical asymptote, the domain, and the range, count as 4 separate problems to the total, so that if you miss one of those, you've missed 4 parts. So go back and repair those. They'll be open all semester long. Go back in and improve those scores, especially you, Tanisha, because you know what you're doing on those. And anybody, if you don't, email me, text me, call me. I'll help walk you through it. Also come to class at Blackboard Collaborate. We'll have, class. I'll be there. You don't have to be there. It's optional. But if you're getting stuck on these, let's go through them. Okay, let's see what we can do about finishing these up. Let's see. Let me get a fresh piece of butcher paper here, or newspaper, or whatever the heck this is. This is still my 4.2, logarithmic functions. There we go. Let's look at number 19. We probably should have stuck around on that other page for number 19. Didn't recognize that. They're asking you for what is the domain for h of x equals log base 3 of x plus 7. So let's talk about that briefly. You know what a logarithmic curve looks like. It'll go through 0, 1. It's doing something like that. That's the basic curve for a logarithmic. Now, if this is x plus 7, you know that's a liar. So it's going to go minus 7. It's going to back up 7. So this point is going to go 1, 2, 3, 4, 5, 6, 7. And that's where the belly button will be. This will be something like that. This will be doing something like that. Okay. With the vertical asymptote running along here. So they're asking you for what is the domain. The domain of this thing is going to be what does the blue one use up on the x-axis. it starts right here. -1, -2, -3, -4, -5, -6, -7. That number matters. That's where it starts. So the domain begins at -7 and goes on out to infinity. It'll always be where you plop in this. So this is where our 0, 1 is, 7 units away, but remember we take up 1 more. So it'll just match that number. Okay, now we're going to play around with numbers again. Let's see. Let's look at log of 10,000. This is a common log. It doesn't tell you what the base is. It's understood to be a 10. So they're asking you, what do you have to raise 10 to make it be 10,000? It's an understood 10 there. So let's set it up for an answer. 10 to the x power will give us 10,000. So 10 to the second power, that's 10 times 10. 2, and those two zeros match. 10 to the third power, that's 10 times 10 times 10. That's 1,000. 3 is the exponent, 3 is the number of zeros. So 10 to the fourth will give us what we were looking for. What do you have to raise 10 to make him have 4 zeros? You have to raise him to a 4. So x is a 4 there. How to do that on your calculator? It's pretty easy. Let's see. Just try it. 10 raised to the third power. Nope, that's not what we wanted. 10 raised to the fourth power. Yeah, that's what we wanted. So the exponent is 4. Don't forget you can also use this 10 to the x power. Just do second and hit the log button and then try that 4 and it gives you 10,000. So we're good there. Number 21, we've got an exponential. This is not a logarithmic problem. This is an exponential. It's got a number raised to an exponent. And I get it, that it sure as heck looks like a logarithm because you see that log there. But log has got to be on the ground for it to be a logarithmic when we can do our circle. This is just an exponential problem. We still need to find out what the answer is. So let's turn it into a log problem. So log, there's a base 10, so we know that's going to be common logarithm. We know that the exponent will always be the answer. So I'm going to put log of 54 out there. This is also a common logarithm, so we know there's a 10 there also. And then this spare number goes right there. So log base 10 matches. When the bases match, the big numbers match. So x is 54. So 10 raised to the log of 54, common log of 54, will give you a 54. I get it that you don't understand a lot of this. That's not necessary. We're just playing around with some of the things. You know, you'll pick up some things. You don't have to completely understand every stinking bit. You just have to be able to play with it. If you go further in math, you'll get it again in some areas. Okay, what'd I do there? Okay, so this is just a continuation of number 20. This is 21. Number 21, the percentage of adult height attained by a girl who is X years old is modeled by this function. F of x equals 62 plus 35 times log x minus 4. That's a common log because it doesn't have the indication of the base there, so you know it's a common log. Okay, that mess there, that means probably nothing to you, is how we can predict the percentage of adult height that a person has reached as long as they're between 5 and 15 years old. So a child. This will be the percent that the person has reached. And all we need now is an X. We need to know how old the child is. So let's do F of, what do we have? We have this little person who is at age 10. I had to write that in there because I messed it up. If I were printing it out for you and leaving it on a table for you, it would say at age 10 at the last of the problem. See, I've written at age 10 there. You don't have that on your form because yours is just an original copy. So write in at age 10. We have a 10-year-old girl. So we're going to grab the function that we're calling f, and we're going to plug in a 10 everywhere we see an x. And this will give us the percent of her adult height that she has reached at age 10. So plus 35 times the log of 10 minus 4. Let's do the parentheses first. 62 plus 35 times log of 6. So we're going to take the common log of 6. So grab your calculator. Let's go to the common log button. It's this first one here. So log of 6 gives us that mess. Leave that in your calculator. So f of 10, we've got this 10-year-old girl, and we're trying to figure out what percentage of her height she has reached. Log of 10 we just found to be 0.778 and some change. So let's turn around right now and multiply that times 35. Times 35. So f of 10 equals 62 plus 27.24. F of 10, we'll add these together. And we get 89%. So at age 10, she has reached 89% of her adult growth. Most of the way at age 10. And you know, that's just rough. We all know stories where people were little bitty bitty and then they shot up. Or people that shot up by the time they were in 5th grade and then didn't grow anymore after that. So it's just a general, see if you can figure out how to work the problem. All right, let's finish this up. Number 22. Are we still on the screen? I don't even know what that is. Let me look. Oh, low battery. Got a low battery there. I do not know how much you didn't get. Crap. Let me get my... Okay, I had peeked every once in a while, so I know that you had it at the place where we were talking about needing age 10. I know you had that. I know you had the screen then. So f of 10, I put in log of 6, so that's just log of 6, and that gives you this 0.778. Multiply it times 35, and you get this 27.24. Add it to 62, and you get 89% of her growth that she has reached, and blah, blah, blah about how people grow. Let's look at simplifying natural log of e to the 12th power. Okay, we know that the base down there is an e, because if it says natural log, we know that that's the base. Common log has a base of 10. This one has a base of e. We want to come up with an answer, so let's say equals x. Let's do our little circle. E to the x equals e to the 12. When the bases match, the exponents match. So x is a 12. Number 23, we have to simplify the natural log of 1 over e to the 25th there. Move down. Okay, same game. We've got a natural log happening here. So we want to put an e right there because we understand that that's an e, that the base is an e. So e to the x equals 1 over e to the 25th power. So we have got to raise up this e to something to make him look like this. So you know the x is going to have a negative on him. That's how e is going to get to the denominator. And then it'll just have to be a 25. So x equals a negative 25. That negative says move me, move me, move me. So we move him down there. And then we have the same thing that we wanted to get. 1 over e to the 25th power. And then number 24 is just loads of fun. I mean, seriously, it is. There's some interesting parts with number 24. Let's see what we can do here. I think in this one, you are asked, like number 20, you're asked not to use your calculator, and 22, you're asked not to use your calculator. Let's see, 20, don't think we did. This one we did not. 22 is asking you not to use your calculator. We didn't need to use our calculators there. And I think 24 does also. You know how that goes. Let's see what we can do. Let's look at log base 2 of 128 minus natural log of 1 over log base 6 on the square root of 3 of 108 minus log of 0 point, and then 1, 2, 3, 4 zeros, 1. Okay, we're going to come up with each of those and then put them over here. So let's start with log base 2 of 128. I looked at the answers to see how they wanted you to do it without a calculator, and they said things like, well, you can see the answer is. Well, no, you can't see the answer is. They can see it. Let's see, 2 to the x equals 128. Grab your calculator and play around with it. 2 to the 5th is 128. Nope, we need more than that. 2 to the 6th. Nope, we're getting there. We need one more of those. So 2 to the 7th equals 128. So we've got a 7 for this piece. So the first part of this numerator, log base 2 of 128, is a 7. Then a minus sign. Let's look at the natural log of 1. Again, let's create this little problem. We know that we've got an e down there, and we know we need an x. E to the x equals 1. Well, what would the exponent have to be in order for it to raise this number, which is like 2. Ooh, I got dirty fingernails. We're out doing yard work. Sorry about that. E to the x, so x is going to equal a 0. E to the 0 power equals 1, so we got a 0 there. Let's work on the denominator. Log of 6 on the square root of 3. I've messed that up. Log base 6 on the square root of 3 of 108. That's what we're working on. Let us set that equal to x and see what we can do with that. So let's do this kind of thing. 6 on the square root of 3 to the x power equals 108. Okay, we've got a 1/2 for this, so it's 6 times 3 on the 1/2 raised to the x power equals 108. Anytime you've got a radical and you're working with logs, you want to convert it to an exponent. And now what we want to do is just try numbers. Let's say this is a 2. Let's see what happens if that exponent is a 2. So let's try squaring it and see if we can get 108 out of that. You still on here with me? Let's see. I'll pull it further in. So, I don't know if I lost you there. I need a way to, need bells to go off when I lose you. So 6 radical 3 to raise to the x power will give us a 108. Then we're going to change this radical 3 to 3 to the 1/2 power. Now let's just see if 2 will work. So 6 squared is 36. 3 raised to the 1/2 squared, that's an exponent raised to an exponent, that's multiplication. Half of 2 is a 1, so this just becomes a 3. And sure enough, 36 times 3 gives you 108. So there's our good guy, the 2. So this log base 6 on the square root of 3 of 108 is a 2. Then we've got a minus sign, and let's do our last little piece. That's a common log, so we know there's a 10 there, of 0.12341 equals x. 10 to the x power equals this number, 12341. Okay, so what this number is, I don't know if you remember, but, well, we know it's going to have to go down. We know that x is going to have a negative on it. That's the way we're going to get the 10 to the bottom. So 10 to the -1 will give us 1 over 10, which is 0.1. 10 to the -2 will give us 1 over 100, which is 0.01. So the exponent is equal to the number of numbers. 1, one number. 2, two numbers. 10 to the -3 is going to give us 1 over 1,000, which is 0.001, 3 numbers. we need 1, 2, 3, 4, 5 numbers. So 10 to the negative 5 is going to give us 1 over 10,000, which is the number we're looking for here. So negative 5 is what we're looking for. That's the answer. X equals negative 5. So let's put it up here. 7 minus 0 is the numerator. 2 minus negative 5 is the denominator. Plus a plus. We get 7 over 7, which is 1. So those 4 problems give us an answer of 1 for the final thing. Send me a text, call me, do what you need to do. Let's get these done, and I will see you in class if you have any questions.